No, actually, it just it's okay first of all. Like, in second presentation, he added some slides about more details about foundation
I didn't add anything
it's okay.
because I have some other things. Can we start now? Yeah, I will just focus on some specific things. Yeah. So, but I will try to just briefly introduce my uh, work here in a simple way. Yeah. So, I try to identify some problem in weekly supervised learning. Yeah, because I will have to show something here. You know, AI, we discussed many times, and everybody knows for now. Before, they used to use some logics to determine something like if functions, like that logician, and then, but today we instead use data for prediction. So let's look at this, for example. We have, for data, always have like numerical data you can have like this. I think you've seen it. It's a famous data set for Titanic. So you have like age, name, and so on, and survive. I think for Titanic data set you have something like this. So there's always something like survive, death, and something, some kind of output for numerical data. So in this case you have some many features here that will give you a corresponding output. This is numerical data, and then you can also have for patch images. You can have this patch image is maybe classified as necrosis. It can be classified as cancer level 1 or level 2 and so on. Yeah, for example. So in most cases, you will see that the data that you manipulate somehow may have either a label or it doesn't have at all. Yeah. So, but if it doesn't have, you have a certain behavior. I think famous is a K-means algorithm like this. K-means algorithm. So you take some kind of data and then you try to do some regression and make two classes already to try to say, okay, this whole data set I'm seeing similarity here and here, for example, for the K-means. That is unsupervised, but when you have this label, it's supervised. Recently, when we had the other discussion, we mentioned about some very big slides. Very big slides. So in the very big slides, it's difficult to say exactly which slides, what is the label of this slide. Sometimes it becomes difficult. Because saying that this slide is cancerous, it means that they have evaluated all these patch images. Sometimes a 512 by 512 or 224 by 224 is small. But when you go to an image of more than, they talk about 3 gigabyte, just one image with very huge size, 300,000 by 300,000. How do you expect a pathologist to analyze and try to get a final response? It becomes a little difficult. I will show you something. So you will see, in the beginning you always have from digital pathology image, you have something like this. This one, you have an image like this. So, but originally when we started with patch images, you have this patch image belongs to a class. If it's cancerous, then cancerous. But in these cases, look at what happens here after prediction. We have, in this same image, we have some parts that are tumor, another part that is another class, and another part for another class. So here we have 3 classes represented here. So in this case, we begin to ask ourselves, but what is the real label of this image? Which label do we give? Because in the beginning, we know that this data is survive. This data is dead. And this patch image is, it has a corresponding. But in this case, we don't know. This is what I try to work on for my cases. How do we call it? Because we don't have a full supervision, the levels, so we call it weekly supervised learning. Weakly supervised, it means that there's already some kind of ambiguity in labels. So the new paradigm is like this. This is what used to happen, or how we came across this problem. I said we use whole slide images before. In a simple way, what you do in the laboratory now, most people use patch images, very small size image. That's what you use to train your models. But now, whole slide image, very big. It exists in digital pathology and also geospatial images. You remember Google Map, as you are zooming, it gives more parameters, and so the Google image also is same. Yeah. But our problem is, since we need to train this one, what is the label we have to assign here? Yeah. Because if we give a wrong label, and then we give a wrong label, and then we are using some kind of unsupervised, so in the beginning, it will bias the clustering. Because I'm saying this is cancer when it's not cancer. So it's making the slides to be very distant. So we have to be careful when we are assigning a label at this point. For example, now, when we started in our project, it used to happen like this. So you have these slides, and then the pathologist will do this. He will just come here and do like this. And he will write this and give a class. It can be necrosis, for example. There are many cancer classes, so he can do this and give a class here. So once he gives the class, then you have to train using it. In weakly supervised learning, one of the advantages is that we don't need the whole annotation. So there is something that they call this slide level annotation. So we just decide that this slide will be considered like this, even though we know that some other classes are present inside. So we can decide like this. Then, if it gives necrosis, so we try to run like that with some classes in our project, but we discover that in some cases you train the model for long, it doesn't change. There's no good results and something. Though there are some other problems that can cause that kind. But also, one of the things is that this label may be wrong. This is why I started my research. Because if the label is wrong in this case, it means we are not clustering the correct slides in the various packages. I want to do a binary classification, I need to put this class and this other class. But the fact that I'm putting one class here, taking this image and putting in the other class, you have to make some kind of bias and reduce the effectiveness. So if you look, this weakly supervised level, it just has to give to this whole slide image some slide level. The slide level, some people just give, oh, this is necrosis, so I will call it like this, because pathologists annotated just this area. But what if all the rest was normal? Is it still right that it's necrosis? No, it becomes wrong. So we need to really think about what is the exact slide level we need to assign here. The fact that he analyzes here and does not analyze the other parts is also a problem, because it may also cause some problem in the future. So we need to perform something to get the correct slide level before we proceed. So in this case, I try to use only this Tumor-Stroma Ratio in colon cancer. But resectable colon cancer means a cancer that can be diagnosed and then treated by operation, surgical operation, for example. So, but this tumor ratio, tumor-stroma, is tumor is tumor already, you know what can make somebody die, and the stroma is like the flesh, normal part. But we try to evaluate what portion of stroma is inside the tumor area. And then in clinical practice, it is proven that if that stroma is high, then the patient will not stay long, he will die. So it's associated with the prognostics of the disease. So that is why they check. And why is it important? Because in this tumor-stroma ratio, I can easily evaluate what is the proportion of tumor and what is the proportion of stroma. And from there, I can give a level by maybe majority voting, like which class is dominating, for example. This is the colon. Any cancer that attacks this section refers to the colon cancer. Now, in weekly supervised learning, you have in the TSR, this tumor-stroma, you can see that it's a very big prognostic for evaluating. So generally, when you have performed the TSR, it's something similar. I think we did like it's something like this. TSR is the stroma in the tumor plus stroma in percentage. It's easy to understand this. So we look at the proportion of stroma inside the tumor microenvironment, for example. So if you have this value, once it's less than 50%, you can qualify as a stroma low, or more than 50% is a stroma high, for example. But however, if you have a high value of a lower TSR, goes for a worse prognosis. A lower TSR is a high stroma value. Yeah. So now, the supervised learning techniques don't work in this case for one reason, because the slide is so big. Yeah. And in unsupervised learning, we must use the slide level label because it's important. And then labeling now is a problem, so we need to understand, because I said before, the pathologists need to annotate just a region of interest, and we use it as a whole slide level, but it didn't show good performance. I will demonstrate it now. Now, in weekly supervised, there are many strategies or ways that they use to treat some problems. For example, one of the ways, and most famous, I think you will see many papers on it, is a multiple instance learning. Multiple instance learning. So in the multiple instance learning, you have what they call a pixel-based prediction in the patch-based, but in this case, in multiple instance learning, they try to restructure whatever we have. So whether be it any kind of problem, they try to make it in a way. So in each way, we have to always assign something like a bar and another thing like instances. So there are at least two levels. So we have a bug there. Like this whole slide image, we call it a bug. And each item inside we call an instance. And then it depends on your representation, because it's your representation. So MIL represents a whole slide image as a bug, and then it represents the patches inside as instance. So how do we perform the final classification? Because the end is that we want the back level classification in multiple instance learning. But to do the back level classification, you need to do the instance level. First of all, you have to start from the lowest item until you arrive. So you will see some other papers now. What they do is this. Originally, this is what MIL wants. So you have bug and instance. So this one I said it can be 300K by 300K. And this one is maybe 256 by 256. Yeah. So in this case, look at what happens. I want to predict this slide, which is very big, 300 by 300, but I'm trying to look at predicting each instance and then try to come back on the back level. This is how it works in a general way. If you read, you will see what it is. But some people do like this. They can create different levels of instance. So they can say, I will do a 512 by 512, and after I will go to 256, and after 128. Because the higher you go, the higher you create instances, and you are more precise in your prediction. And inside, any kind of algorithm can intervene. Why not? Many big MIL machines use support vector machine, even the decision tree that you know, which seems to be basic, but at the base of the instance prediction, this is what they use inside to do some kind of instance level. So they can have instance level 1, instance level 2 until the back. The final goal is to give the back level prediction. So if you read, you will see, they say another paper that handles like this with rat images. You know rat? Yeah, rat images also to do some kind of, anyhow, when you see a case where the labels are not certain, always think about weakly supervised. And one of the ways is multiple instance learning, for example, MIL. And in MIL, you can have the whole thing that is a back, and then you have instances, and you have mechanism to predict the instances and come back to the back level. Yeah. And then another way is the graph-based method. So you use this to connect all the data points, and also the self-training method. What's the meaning of self-training? Very simple though. So you first of all perform the training. You have a few labels. So you use that one to perform the training. And when you perform, you do some testing now. On the testing, you have a new label predicted based on the data, and you add it back to the training set, and you retrain again, and so on. That kind of situation. But when you engage into weakly supervised learning, you have to understand there are some very big issues. Like now I was just talking about the slide level, but you understand what it is already. This is the annotation we give to this slide. And then we say it can be very subjective. So some of the problem is that, just imagine this pathologist came and annotated here, and he gave to this slide the necrosis. Imagine another pathologist came and annotated here, and he discovered this is instant normal. What happens? So the pathologist that did this one will give this slide necrosis, and this other one we call it normal, which is already ambiguous. How do you train it? It shows that the result will be biased somehow. That is why we really question, but how do we use effective whole slide image label? It's very important. So at this point, different pathologists may have different interpretation for one slide. Sometimes because they don't understand the thing the same way, or still they can do assessment on different regions of interest, and then they give various labels. So in most cases, you don't have any ground truth information. In most cases, like in case of metastasis. Metastasis is advanced stage of cancer traveling to the body. Maybe if you have breast cancer, it finds its way to the liver. The breast cancer cells travel to the liver, it makes a metastasis. So in this case, sometimes they have clinical, you go to the hospital, they will take the blood, and they will test the blood and tell you that you have some value that shows you may have metastasis, cancer metastasis. It doesn't mean you are developing liver cancer. No, you are still a breast cancer patient, but it has developed and traveled in your body. And in that case, sometimes it's hard for the machine learning algorithm to know that this is a breast cancer cell that went there. They don't know. So they can only say that it is metastasis, but they don't have any granularity on the information. That's a ground truth. They cannot do any annotation from there. They'll start to work. And in all those cases, you may also have noisy and irrelevant data. All these cases are very important to apply weakly supervised learning. So I asked myself, like, in a simple way, this is really clear. This is a slide. He annotated this place as a tumor slide. So I would think, well, what about this region? What if it dominates over the other? What will I say? Is it tumor? I don't know. And I look at this also. This is a region where he worked, and then he annotated this as normal. What about this one? And what about the other region beside? Is it really good to call this slide normal? I don't know. And it becomes more confusing when you have many classes. If in the binary classification it gives you many classes like this, I have necrosis, I have a tumor, and normal. How can I assign a slide level here? This is my question, my problem. Yeah. So the first thing is that I have to do some kind of accurate slide level prediction by majority voting. Yeah, in this case. But since it's an academic work, the first thing is that I want to do assessment of TSR, because I work on colon cancer. This TSR we already explained that is fundamental for prognostics of a patient. So if I succeed to do this in a good way, it will give me some clinical indication for that patient first, and secondly, I can use it for annotation and do some other things. So the main objective is to show that if I have the best corresponding slide, it can resolve into good result after training, for example. I just focus on one thing now. It was TSR in colorectal cancer. No other use case. It therefore means that another person may try in another case and it will change some kind of things. Yeah. But from the literature, you can see clearly that many people already underline some labeling challenges in weekly supervised. Already they think about it. This kind of problem exists. So they think, and then they also suggest in many ways some kind of solution. So, yeah. How do I solve this problem? I solve it by using two things in a simple way. The first thing is that I have to develop a fully supervised method that I will use to detect that label that I don't know, I'm questioning. I will use this fully supervised method to detect the label. And if I succeed to get the label, I will go now in a weekly supervised technique like MIL and test it. If by testing in MIL, I will see if the labels that the pathologist gave and the one that I predicted, how are they? Is it better to use mine or his own? Is there effectively a problem? That is why I asked this question here. So I need to know, is there a problem in this slide level labeling? And then I have to answer this one. So you know exactly, if I use a fully supervised method, I have 3 data sets here. These 2 data sets, this one is just patch images, 1,000 patch images. And then this one has patch images plus marks, segmentation marks. So if I talk about segmentation mark, it means that we really want to show the segmented area, semantic segmentation. And here, I downloaded extra 88. There were 90, but 2 slides were corrupted. So it resulted in 88 slides of colon cancer. This 88 slide came already with some kind of annotation, normal and tumor. So I will show you what happened to those ones. I downloaded like that from a public data set. So this is the data. And so this one is the data, yeah, and then this is the prediction, the segmentation data set. Yeah, and some consideration you can do depending. So maybe sometimes you can talk to pathologists or you read in some other papers and you try to see. Like for example here, my interest is to analyze TSR. This TSR is tumor and stroma. So here I have the tumor class here, for example, and then all these ones are some other classes. And then here I can identify the tumor, the stroma in the tumor slide. So what am I doing here? In this case, I have to, consider all these classes as a normal class because they are not of interest. What I need is this tumor. I need to know that I have a tumor slide so that I can apply this segmentation technique and try to dissociate. This is why we call this stroma. It's a stroma-associated tumor. This one. Stroma-associated tumor. It means that it's a stroma that is inside the tumor. So we only find it from this class. So if we classify something as normal, we put aside, but the other one we need to check carefully. This kind of consideration now, and then for the deep learning model training, 3 models were used. Because I need to do a normal, I will show you. Just give me. Oh, I'll show you some flow here. Yeah, this one. Okay, this is what I do each time. When I take a whole slide image like this one, I will do some patch. I will make some patch, and then after the patch, I will try to check if the patch is normal or tumor. So if I have a normal patch, I don't need to do anything again because it's not of interest for me. But for tumor patches, I have to try segmentation. This is the first thing is classification. If it's normal, I don't use it. But if it's not normal, I have to do segmentation. On segmentation, I have to determine the tumor area and the stroma-associated tumor area also. And then from there, I will check, is there any other patch? I will do the same thing for all the patches of the whole slide image. And after I can do the reconstruction, so I can map it back again to see what area represents what exactly. So I have like normal here, tumor and tumor-associated stroma. for example. So this model, the classification model was done using efficient net. And then the segmentation model, in the segmentation model, we try to apply segmentation-based model. So this efficient B2 unit is very famous for segmentation. So efficient net B2 and TransUnet were applied, but still at this level, so this is efficient net for classification, and this is TransUnet. The TransUnet, its own advantage is that, changes in this encoder. He uses CNN and the transformer in the encoder before he does reconstruction. But after we try to realize something, if I use the TransUnet and the efficient net, I have a feature map here. This is 256 by 256. After aggregation, it increases the segmentation classification results. Yeah, so that is why it was better to do this one. So this other one is novel architecture. The name is efficient TransUnet. So there is efficient and this transformer that were combined to get this one through aggregation. And then after doing this, it's easy to get. When you do this, you can get this kind of prediction. So when I use those models, I can easily do this kind of prediction. And I do reconstruction, I can have this. Like this one gives 33% CSR. So it's a stroma low here. And this one gives 52% is stroma high. Okay? So if I'm talking about tissue, tumor and stroma, I will label this one. I will call it tumor slide. This is the best label for this one. And I will instead call this one stroma. Because stroma is high. It's more than 50%. It's dominating in all the cases. This is how I give the correct label, by majority voting in this case. So now the segmentation was done by that model, and you have, when I give those labels now, I come here. After giving the labels, I use this one. It's closer constraint attention multiple instance learning. So this is a weekly supervised framework that's existing already. So I use this one to try. I want to do prediction of labels. So this one is what I will use to try. So in this section, I try to explain what it is and the kind of architecture. You always see the same thing, like box and everything, classification, until the final level. So when I do this, I have the results already. And then look at what happens now. I have taken 10 random slides. So in these slides, I perform segmentation and I have a pixel area here. So I have a normal area. I think it's normal region area, this one. And I have a tumor region area. And then I have all pixels. Yeah, the total pixels there that I have. They are expressed in pixel. Yeah. So look at what happens. In those 88 slides that I downloaded, this is the original label. Original label, this one. But for these 4 slides, 1, 2, 3, 4, you see that here it was tumor originally, but it's predicted normal. And here is tumor is predicted normal. Here is normal is predicted tumor, and here is tumor is predicted normal. Why it happens like that? I explained. Maybe the region that I used, why assigning this wasn't the best. This is one of the reasons. Or maybe they did it in a subjective way. So it did not totally match with what was supposed to be. But at the prediction here, with the model, with the segmentation efficient TransUnet, we see that when we compare the pixel area, by majority voting, we have some different levels. So in this sample, we have 1, 2, 3, 4 that are different. So in 88 slides, 15 were different. 15 slides. So I have 15 slides. It therefore means that I have to do some training. Yeah, in those 2. So when I use those 2, I try to train the original label and the predicted label in claim. For the predicted label, I have some accuracy of 75% with predicted label. So if I make my slide using the predicted label, it gives 75. But when I use original label, it's 72. So there's like 3% increase in accuracy And it's also same here. In the A, you see 4% increase. It's very significant in digital pathology. Even 2% is also good. So 3% is somehow good. My question is not to know whether this weekly supervised approach is good or not. I just want to make my label and come and try it somewhere in any approach. So I choose this one randomly, and then now I can have some results that show different. It shows that effectively, in my question, was it a problem or is there any problem in this original label? Yes, there is. And also, it shows that there is an increase in terms of performance. And why? It's explainable because the predicted set makes some more similar clusters in the beginning of the training. When I did this, what I try to do later is look at this. This is a whole slide image, and then this is another prediction. But in this case, I didn't label it as normal and tumor. Like in that case, I labeled it as stroma and tumor. But this one, only pathologists can give explanation. But the minor explanation I can say is that, look at this area. It's a tumor area inside, it's a stroma area inside the tumor. This is what they use to estimate TSR in the past. They don't care about this one. They care about the stroma inside the tumor. So that's why I say only pathologists can appreciate. But the weekly supervised helps to give this attention, the heat map, that helps him already. It's also good because if he has this, he doesn't need any annotation. But we need to give correct annotation. That is one of my conclusions. We need to give very accurate slide level label. And then we perform this like this. From there, he can give interpretation. Yeah. So this is somehow what I did. But in any case, I feel that if you want to try this in another case, like maybe breast cancer or something, you need to retrain again with another set of breast cancer image because you cannot transfer this one, maybe. That is a limitation of this work because you need to apply for the specific use case. But my real point is that there is a big need to check the label. Yeah, and that was what I demonstrated. Thank you.
You said that while giving the patches, it might not give the whole picture of the image and it might not predict work. And in this case, you said that it's kind of sliding the image, but like giving labeling or something like that.
Slide level label.
I couldn't understand that part.
Okay.
In that,
Yeah, the slide level label. Okay.
But while you are training, you are giving the patches, right?
Yeah. No, I'm not giving the patches, I'm giving the whole slide. This whole slide, yeah. This, the whole thing. But I train with the patches just when I wanted to obtain the labels. That is why I say I'm using two things. A fully supervised approach to obtain the correct label, and a weekly supervised approach to try whether the predicted or the original labels are working differently. You don't still get it? Okay, wait, I will show you something.